Section 7.2, Effective Nuclear Charge. Because electrons are negatively charged, they are attracted to nuclei, which are positively charged. Many of the properties of atoms depend on their electron configurations and how strongly their outer electrons are attracted to the nucleus. Coulomb's law tells us that the strength of the interaction between two electrical charges depends on the magnitude of the charges and on the distance between them. Thus, the force of attraction between an electron and the nucleus depends on the magnitude of the net nuclear charge acting on the electron and on the average distance between the nucleus and the electron. The force of attraction increases as the nuclear charge increases, and it decreases as the electron moves farther from the nucleus. In a many-electron atom, each electron is simultaneously attracted to the nucleus and repelled by the other electrons. In general, there are so many electron-electron repulsions that we can't analyze the situation exactly. We can, however, estimate the net attraction of each electron to the nucleus by considering how it interacts with the average environment created by the nucleus and the other electrons in the atom. This approach lets us treat each electron individually as though it were moving in a net electric field created by the nucleus and the electron density of the other electrons. We can view this net electric field as it results from a single positive charge located at the nucleus, called the effective nuclear charge. It's important to realize that the effective nuclear charge acting on the electron in an atom is smaller than the actual nuclear charge because the effective nuclear charge also accounts for the repulsion of the electron by the other electrons in the atom. In other words, the effective nuclear charge is less than the nuclear charge. Let's consider how we can get a sense of the magnitude of the effective nuclear charge for an electron in an atom. A valence electron in an atom is attracted to the nucleus of the atom and is repelled by the other electrons in the atom. In particular, the electron density that's due to the inner core electrons is particularly effective at partially canceling the attraction of the valence electron to the nucleus. We say that the inner electrons partially shield or screen the outer electrons from the attraction of the nucleus. We can therefore write a simple relationship between the effective nuclear charge and the number of protons in the nucleus. The factor S is a positive number called the screening constant. It represents a portion of the nuclear charge that's screened from the valence electron by the other electrons in the atom. Because the core electrons are the most effective at screening the valence electron from the nucleus, the value of S is usually close to the number of core electrons in the atom. Electrons in the same valence shell do not screen one another very effectively, but they do affect the value of S slightly. See a closer look on effective nuclear charge. Let's take a look at the sodium atom to see what we would expect for the magnitude of the effective nuclear charge. Sodium, atomic number 11, has a condensed electron configuration of neon 3s1. The nuclear charge of the atom is positive 11, and the neon inner core consists of 10 electrons, 1s2, 2s2, 2p6. Very roughly then, we would expect the 3s valence electron of sodium atom to experience an effective nuclear charge of about positive 1, as pictured in a simple way in figure 7.3a. Figure 7.3, effective nuclear charge. In A, the effective nuclear charge is experienced by the valence electron in a sodium depends mostly on the positive 11 charge in the nucleus and the 10 minus charge of the neon core. If the neon core were totally effective in shielding the valence electron from the nucleus, then the valence electron would experience an effective nuclear charge of positive 1. B, the 3s electron has some probability of being inside the neon core. Because of this penetration, the core is not completely effective in screening the 3s electron from the nucleus. Thus, the effective nuclear charge experienced by the 3s electron is somewhat greater than positive 1. The situation is a bit more complicated because of the electron distributions of atomic orbitals. Recall that the 3s electron has a small probability of being found close to the nucleus and inside the core electrons, as shown in figure 7.3b. Thus, there is a probability that the 3s electron will experience a greater attraction than our simple model suggests, which will increase the value of the effective nuclear charge somewhat. Indeed, the value of the effective nuclear charge obtained from detailed calculations indicate that the effective nuclear charge on the 3s electron in sodium is about 2.5 protons. The notion of effective nuclear charge also explains an important effect that we noted in section 6.7, namely that for a mini-electron atom, the energies of orbitals with the same N value increase with increasing L value. For example, consider a carbon atom, which has an electron configuration of 1s1, 2s2, 2s2, 2p6. The energy of the 2p orbital, L equals 1, is somewhat higher than that of the 2s orbital, L equals 0, even though both of these orbitals are in the n equals 2 shell. The reason that these orbitals have different energy in a mini-electron atom is due to the radial probability functions for the orbitals shown in figure 7.4. Notice that the 2s probability function has a small peak fairly close to the nucleus, whereas the 2p probability function does not. As a result, the electron in the 2s orbital is less effectively screened by the core orbitals than the electron in the 2p orbital. In other words, the electron in the 2s orbital experiences a higher effective nuclear charge than one in the 2p orbital. The greater attraction between the 2s orbital and the nucleus leads to a lower energy for the 2s orbital than for the 2p orbital. The same reasoning explains the general trend in orbital energies of Ns is less than Np is less than Nd in a mini-electron atom. Finally, let's examine the trends in effective nuclear charge for valence electrons as we move from one element to another in the periodic table. The effective nuclear charge increases as we move across a row or a period of the table. Although the number of core electrons stays the same as we move across the row, the actual nuclear charge increases. The valence electrons added to counterbalance the increasing nuclear charge shield one another very effectively. Thus, the effective nuclear charge increases steadily. For example, the 1s core electrons of lithium shield the 2s valence electrons from the 3 nucleus fairly efficiently. Consequently, the outer electron experiences an effective nuclear charge of roughly 1 . For beryllium, the effective nuclear charge is experienced by the 2s valence electron is larger. In this case, the inner 1s electrons are shielding a 4 nucleus, and each 2s electron only partially shields the other from the nucleus. Consequently, the effective nuclear charge experienced by each 2s electron is about 2 . Going down a column, the effective nuclear charge experienced by valence electrons changes far less than it does across a row. For example, we would expect the effective nuclear charge for outer electrons in lithium and sodium to be about the same. Positive 1 for lithium, positive 1 for sodium. In fact, however, the effective nuclear charges increases slightly as we go down a family because the larger electron cores are less able to screen the outer electrons from the nuclear charge. In the case of the alkali metals, the value of the effective nuclear charge increases from 1.3 for lithium to 2.5 for sodium to 3.5 for potassium. Nevertheless, the increase in effective nuclear charge that occurs moving down a column is smaller than the charge that occurs from moving horizontally from one side of the periodic table to the other.